I have it. So, good morning, everyone, and welcome to this new EUPEX webinar. I'm Pascal. I'm the EUPEX dissemination leader, and I will be your host today. So today's topic is going to be scientific workflows in the heterogeneous era, not area, sorry. And before I hand over to today's speaker, I wanted to say a few words about this series of webinar, because this webinar is one of a series. We are organizing webinars so that our researchers can share their results and the lessons learned during the project. So we organize monthly webinars, and we started with the applications and the tools that were analyzed and enhanced under EUPEX. So the recordings of the past webinars are available on our YouTube channel, so you can easily find them and listen to them. We had some very good webinars, and I really encourage you to visit our YouTube channel. The full list is under the link shown on this page, and our next webinar will be at the end of March, and it will be about vectorization of FEM kernels. So that's Espresso FEM, and IT for Innovation will be the presenter. And then we'll have software stacks, we'll have CA's Ocean in April, and Parastation Modulo by Partech in May, but I don't have the date yet. So that's for the upcoming webinar, and now we'll get to today's topic. If I can manage to switch to the next slide. Yeah, okay. So this is our fourth webinar, and I'm very happy to welcome Jacopo Colonnelli from the University of Torino, who is going to present StreamFlow today. So Jacopo, welcome. I'm not going to read your bio. I think everyone can read it, but we are very happy to have you today. So the floor is yours, Jacopo. Feel free to share your slides. I will stop sharing mine.
Thank you very much for the introduction. I will share the screen. Okay, just to confirm that you can see it.
We can see your slides.
Okay. I'd like to do it in presentation mode, so you can see them full screen.
Yes, full screen
and
now.
they are
Thank
changing.
you. Thank you.
Okay.
Yes, they are.
Perfect. Thank you very much. So today I will talk about more of a tool to enhance the applications. So this is not a EUPEX application, but is a tool which is called StreamFlow. But instead of just talking about the StreamFlow Workflow Manager, I would like to give a general overview on scientific workflow concepts and how they should be adapted to meet the requirement of modern large-scale HPC applications, which are far more requiring than some years ago. So when I have a complex task to do, normally what I choose to do to simplify my life is to divide it into smaller subtasks and try to solve them one after the other, the divide et impera logic of the ancient Roman Empire. No? But this kind of abstraction can be also realized in a more formal way by means of the concept of workflow, which is basically a graph modeling a complex workload by means of steps, which are the things to do, and their data dependencies, so the data that each step produces in output and the data that each step needs as input to perform its computation. By this abstraction, every very complex experiment can be described as a workflow, but in reality, workflows are a very generic concept. I can describe a workflow. With a workflow, practically every activity, from washing my hands to make a pizza, to make a data analysis pipeline, to very complex scientific workflows, to also human activities in a business unit, in the business unit of a company. Obviously, since we are a research project and a scientific project, we are more interested in scientific workflows. And basically, the first question should be why I should take the burden to model my experiment as a workflow, because it is some additional work. I have to write my code, I have to test it in production, and then I have to decompose it in submodules, identify the dependencies, and then write it as a workflow. But the burden comes with several advantages. For example, I obtain for free concurrent distributed executions, because if I decompose my experiment into steps and dependencies, I can automatically run in parallel the independent tasks, or I can delegate a tool to do it for me. So I can obtain parallel and distributed execution for free. So this is for performance improvement. Then, if I use a workflow system to run my experiment, I also obtain portability and reproducibility, because instead of compiling the code on my machine or on my data center, I basically write a recipe and delegate the environment-specific aspects of the pipeline to a tool that has been engineered by computer scientists to be able to obtain hopefully the best performances in every execution environment. So I just have to run my workflow and it will be optimized for different execution environment by a third-party tool. And also, probably, if I choose an HPC-ready workflow system, it also solves for me some of the burdens that come when I try to scale from my laptop to a full HPC facility, which is far from being trivial. And so I obtain all these advantages. So take home message, it is worth sometimes to write my experiment as a workflow. But this is no more enough in modern era, in the heterogeneous era, because as we always see while we look at the HPC ecosystem nowadays, we have no more experiments that run on a bunch of homogeneous machines, fully interconnected as before. We have, for example, to support microservice applications instead of monolithic applications. So a single application can be composed by different microservices that must run together and be orchestrated on a complex facility like on Kubernetes or on modular HPC. So we have to support multiple micro applications talking to each other to accomplish a single task, maybe a Spark cluster or something else. Then we have to address modular architectures. So we have to address, for example, the IoT in the compute continuum, but also modular HPCs. So a high-performance computing facility composed of several modules, the big data module, for example, and the accelerator-equipped module. And for different steps of a complex workflow, maybe we have to choose a different partition of the HPC facility. Also, maybe I want to go even further and to schedule some steps on the cloud and some steps on the HPC, for example, to balance high-performance computing and high-throughput computing. But this means that I have to interface my workflow with several independent protocols for authentication, resource allocation, and authorization, and so on and so forth. So this becomes more and more complicated. Then I have to deal with accelerators. So no more simple von Neumann architecture on my CPUs. I have to deal with accelerators, maybe FPGAs, maybe quantum computing. So this is becoming a trend, a hot trend in Euro HPC. So to couple standard HPC with quantum computing. So again, I have my workflow. Some steps may be classical, some steps may be quantum, some steps will be GPU based, some steps just CPU based, and I have to satisfy all the requirements together. And then large scale architectures can be also fully distributed. This is more an edge and fog computing concept, but this could be also true when I move from a single HPC facility to HPC federation. So many HPC facilities for the same workflow. I would like to use more than one data center for my application. I can choose to put somewhere a centralized control plane, but this could slow down could become a bottleneck, so it can slow down the computation. So I would like to have a fully distributed control plane to avoid single point of failures and bottlenecks. Then when I mix the execution architecture, so when I mix cloud with HPC, with compute continuum, I have to deal with different parallelism modes. For example, normally HPC workflows are based on file-based exchange of data. So step one writes a file on the shared file system. Step two reads from the shared file system. But maybe I have some in situ workflow that instead talks through the network. So by streaming the data through the network from one step to the other. And a modern workflow system must be able to deal with different data exchange pipelines, maybe in the same workflow, and possibly without requiring the developers to modify their internal code, because this is time-consuming, dangerous, and people normally are not willing to do it. And finally, this is something that is especially useful for very long scientific simulation. I would like to see interactively what is happening during my simulation. And maybe I would like to early stop some simulations that are diverging or that are not giving the expected results, to leave space for some more useful computations, maybe some refined attempts of my simulation plan. But this requires interactive computation, and also this requires some user interface like Jupyter notebooks. Now, combining Jupyter notebooks and interactive execution with the complexities of modern workflow that I just discussed is far from being trivial. It's very difficult. But still, a modern workflow system should support also this kind of usage path. So, given that we live in a difficult world for workflow orchestration, today I would like to present some of the progresses that we made in these directions. And in particular, some of them are part of the EUPEX project and will be used to orchestrate, hopefully, some of the applications inside the project. So this could be useful also for application providers to take a look at what is the state of the art in this direction now, and see which features could be useful for them. First thing I will talk about is the concept of hybrid workflows and the StreamFlow workflow system that implements this concept. So the state of the art since a few years ago was that a workflow management system targets a single execution environment for a single workflow. So many workflow systems support several execution paths. They can be executed on the cloud or on the HPC or on a local machine. But when I schedule a workflow, I have to stick with one of execution environment. I cannot schedule some steps on the HPC and some steps on the cloud. And this can be a limitation. Also, normally, I require a single shared storage space among all compute units involved in the workflow, because this is a very easy way to exchange data. I put the data on the storage space so everyone can access them. But this is not always true. It is true on the single HPC facility. It is not true between HPC and cloud or between different HPC data centers. Then some more advanced workflow systems allow automated data transfers between different steps, so they relax the single shared space requirement, but still they rely on a single orchestration tool that must be installed on all the compute facilities, and this is not always feasible. And the most difficult part is that all these details are not explicitly encoded in workflow descriptions. They depend on the design choices of the workflow system. So this hinders the reproducibility and the portability of the workflows. What we created is a new workflow model called hybrid workflow, in which all these details are encapsulated directly in the workflow description. So the workflow plan that the user designs also includes the execution environments that will be used and the mapping between steps and execution environment. In this way, a hybrid workflow can be scheduled on multiple heterogeneous and independent computing infrastructures, and then the workflow tool enacting this model is in charge of finding the best way to move the data, allocate and deallocate resources, and orchestrate the computation on top of these kind of very complex environments. This is the StreamFlow, the scheme of the StreamFlow workflow system. StreamFlow adopts the common workflow language open standard as the way to describe the workflow. Then it adopts declarative description files in YAML or JSON to describe the different execution environments, which can be cloud-based like Kubernetes or HPC-based like Slurm, PBS, Spectrum LSF from IBM, Flux, or also simply container-based executions on a single machine. And this execution environment can also be stacked one on top of the other, so it is very flexible on this in this way. Then the execution plan of each workflow is derived from StreamFlow at runtime, and it is able to basically enact a hybrid workflow. The point, the important point of using an open standard like CWL instead of developing our own workflow description is that this does not bind forever our flow to the StreamFlow execution environment. If tomorrow I am not happy to use StreamFlow, I can use another CWL compliant workflow system or create my own. The problem of CWL is that the naive CWL was not ready to execute high performance computing experiments because, for example, it was lacking the loop feature to describe iterative experiments, which are the most diffused kind of workloads in HPC. Think about deep learning, which is deep learning training of models, which is inherently iterative, or multiple refinement simulations, which must run several times up to convergence. These are all examples of iterative parts of our workflow. And this is the reason why we created the common workflow language for HPC working group, which aims to identify workflow patterns necessary to model large-scale scientific applications and then implement the new patterns as CWL enhancement proposals. One of the main achievements of this group is that now CWL 1.3, which is going to be released very soon, will support loops. So this will be one of the main achievements of this work. And then when we support CWL iterative patterns, then we can encode CWL iterative workflows for free on StreamFlow. And so the iterations will be all orchestrated by the workflow system. Then I will present some case studies of StreamFlow. This is the first one, the first experiments we released. We had a bioinformatics pipeline which was running on top of a single HPC facility. But we've seen that while the first and the second steps were very resource intensive, the third and the fourth steps were very naive. They required a few cores and they were not so parallelizable. So we decided to offload them to a cloud partition to free HPC resources for more intensive computations. And we were able to do this kind of offloading to a Kubernetes cluster in a cloud partition, while taking more or less the same make span of the original computation. So little to no overhead in passing from standard HPC workflow to a hybrid HPC cloud workflow. Then we explored a much larger bioinformatics pipeline, which is made of a very long queue of different steps. Some of them are data parallel, so can be decomposed in several instances of the same steps running on different data chunks. And in particular, this yellow one can be decomposed in 250 parallel steps, which can run in parallel. Now we can see that scheduling all of them in the cloud or scheduling all of them in the HPC is more or less the same in terms of performances, but the reasons of the slowdown are different. On the cloud, we run on virtual cores, so we cannot achieve the same performance of the physical cores. On HPC systems, we pay the queue time and the SLARM queue manager overhead, because each step must wait into the queue and then be scheduled, and then the machine must be initialized, and so on and so forth. So we decided to try a hybrid run in which we use both the cloud and the HPC facility, a sort of urgent computing setting, and we are able to achieve a significant speed up. And the nice thing is that all these kind of configurations are very complex to be obtained by hand, but it is just the matter of changing a few lines on the StreamFlow declarative configuration file, and then we can migrate from one execution environment to the other, and also mix them and let the StreamFlow choose where to send each step. So this is all the burden of data movements and synchronization between different facilities and so on and so forth is left to the workflow system. Then we try to explore the possibility to use multiple HPC facilities for federated learning, but this kind of approach can be extended very easily to every workload that has a bunch of independent steps and a final aggregation step that merges all the computations, so the classical MapReduce pattern. And we try to assess the performance of federated learning on top of two different facilities, one at the University of Torino, one on the Cineca Marconi 100 machine that now does not exist anymore. But we were able to obtain a significant speed up by using the hybrid scenario. So we wanted to go even further and try to use two much larger facilities, the Cineca Leonardo facility in the IT4I Carolina cluster, to run a federated learning on top of a very large language model, which is Llama. And this has been executed by means of StreamFlow, acting as the orchestration plan. And we were able to basically obtain also here a significant speed up. And now we are working to extend this kind of experiment on top of practically every machine in the EuroHPC ecosystem. So IT4I, Cineca, Lumi, BSC, Vega, and so on and so forth. And this is an ongoing experiment that is following, is a follow-up of this first attempt. The same thing can be again extended to every scientific simulation that has some independent steps. And we will be very happy to try this kind of approach with, for example, SpecFM 3D Plus into the EUPEX project. Finally, we are using StreamFlow also for end-to-end security. We know that when we move the data from our on-premise HPC to the cloud, we must enforce privacy concerns. And this is not trivial if we go on a third-party cloud computing infrastructure. So we are leveraging trusted enclaves, Intel SGX, AMD SEV, and all those hardware enclaves to ensure data protection not only at rest and in transit, but also during usage by encrypting basically the main memory during computation. And obviously this has an overhead, but we are exploring ways to minimize this kind of overhead, and especially how to put these techniques directly in the workflow orchestration plane. So freeing the user from worrying about this kind of very technical stuff about performance improvement in confidential enclaves. StreamFlow is involved in several projects. Some of them are the EuroHPC projects. Then there was this DeepHealth project, which was a Horizon project. And also it is involved in collaborations with companies and research facilities in Europe and in Italy. We have a collaboration with IBM, which is ongoing, and we also have a collaboration with the LOFAR telescope in Netherlands that is very active on the CWL side, because all the workflows are written in CWL, and we are trying to speed up and introduce hybrid concepts through the StreamFlow orchestration system. So this was basically the part on StreamFlow. StreamFlow is one of the exploitable results of the EUPEX project, so I went a bit deeper inside this into this part. I will be much faster on the other parts. So the main problem of StreamFlow is that it is a centralized control plane. So it has the workflow orchestration plane that is the oracle that knows everything, and it has to be deployed somewhere from where I can reach all the execution environments involved in the workflow execution. This is practical for most of the times, but not for every deployment. And so I would like to have a way to define fully decentralized workflows. And this is far from being trivial, because I need some kind of projection system to decompose the workflow and to give each of the involved execution locations the knowledge of their related portion of the workflow and how to communicate with other involved locations without relying on a central point. This is very complex and requires a very low-level workflow representation. The problem is that all workflow languages are made by humans, so they are very easy to be written by humans. They are very complex to be interpreted by machines. This is why we introduced this scientific workflow intermediate representation language that can translate a high-level human-oriented workflow language like CWL into a low-level machine-oriented representation, and then from this representation I can derive a distributed execution plan where each location communicates directly to the others by means of send-receive primitives. We can see SWIRL more or less as an LLVM for scientific workflows in a way. Then we implemented a compiler called the SWIRL-C, which compiles a high-level hybrid workflow from, I don't know, CWL or Pegasus or Galaxy into this SWIRL language, and then compiles this SWIRL intermediate representation into a fully distributed executable bundle, which can also be optimized for the specific execution environment that I want to use. For example, we applied this kind of translation to the 1000 genome workflows, and we obtained a decent speed up for up to 10 different execution locations. We are now working on extending this kind of representation to different target languages. We use Python for this experiment, but we are going to use also Rust, for example, which is has better performances. And then we will also try to insert more patterns also in SWIRL. Sorry. Then the next thing we worked on is how to unify file-based communication with streaming communications. And basically on this part, the main problem is that again, I cannot more suppose to have a single persistent storage when I enact my workflow. Or even if I have it, I may want to avoid to use it because, as we know, shared file system is often the main bottleneck of modern HPC large-scale applications. For this reason, we basically introduced a way to transparently convert file-based workflows into streaming workflows by co-scheduling different steps at the same time, different subsequent steps at the same time, and transforming file-based I/O read and writes to network data exchange by means of read-write communication primitives, but that are translated into network based communications. And how we did implement this? Basically, we implemented a library called CAPIO, Cross Application Programmable I/O, that is able to intercept POSIX system calls. And instead of sending them to the Unix kernel, CAPIO is able to transform this kind of read-write system calls into several stream-based communication or message-based communication backends, like MPI messages and QTT queues, or even when, for example, I have two large files, even saving them to the parallel file system, so falling back to the file system, but still preserving the possibility to stream the data from one application to the other. Obviously, this has two main advantages. The first is that I improve the computation communication overlap, because I can start reading the data as soon as the first application creates them. I don't have to wait first application to finish before starting the second one. And also, I can, if I rely on in-memory caching of data, I can avoid the overhead of involving the central file system in the execution. Again, we tried this library on the 1000 genome file the 1000 genome workflow. We were able to again obtain significant speed up of the workflow. And recently, we also tried this on astrophysics visualization, data visualization workflow called Visivo. And here we were able to reduce the time of the execution time of the workflow from sorry, the execution time of the workflow, in some cases even of about more than 50%, or even three times in case of the statistics filter. CAPIO is another example of a library which is involved into the EUPEX project, and the integration between StreamFlow and CAPIO to allow transparent stream-based workflows in hybrid scenarios is one of the goals of the EUPEX project. So we are working actively on that. The last thing I would like to talk about is the literate computing part, so the interactive execution part. Basically, the main abstraction which is used to enact interactive workflows is the computational notebook. So Jupyter notebook normally. Computational notebook can be seen as a list of cells called cells. Each cell contains a portion of my program. And I would like to execute my cells as a workflow, but the normal execution path of a computational notebook is sequential. So I execute my cell. It modifies the global state of the program, and then I execute the next cell. And these executions are normally delegated to driver process, which is called kernel in Jupyter notebooks, which can be a Python interpreter, a C++ interactive interpreter like Kling, or many other languages, but still the cells are executed one after the other. This is a huge performance overhead, because maybe I have cells that are not dependent one from the other, but I am not able to execute them concurrently. So if I want to scale, I want to relax this sequential order. And also I would like to maybe be able to treat each cell as an atomic execution step of a hybrid workflow, and then schedule the execution of different cells into different execution environment. One cell on the cloud, one cell on the HPC, one cell on the local machine, depending on the complexity. Plus, I would like to port into Jupyter notebooks all the non-functional requirements that are proper of workflow, of scientific workflows, like portability, reproducibility, provenance, and so on and so forth. To do that, we introduced a way to decompose a Jupyter notebook inside a direct acyclic graph by relaxing the dependencies between the cells, and this is done by code inspection. So this is done automatically by the the workflow system. And then, since I know the dependencies, I can execute some cells concurrently while obtaining sequentially equivalent semantics. So I can preserve the same result up to errors due to the approximations, but still I can preserve the same dependencies of the original workflow while preserving while speeding up the execution. Finally, I can extend the notebook metadata format, because Jupyter notebooks are based on declarative metadata. I can use this metadata to encode additional dependencies between cells, or to encode maybe parallel construct like gather and scatters, or to encode the hybrid part of the workflow, so to identify target execution environment for each of my cells. And finally, I can put all this together and give the users a very beautiful graphical user interface they are used to, which is the Jupyter interface, which hides all the complexities of this approach by means of intuitive web-based interface. So in this way, I can extend Jupyter notebooks from the prototyping phase of our flow to the large-scale production executions of my workflows. And we demonstrated this by executing a very large hyperparameter search experiment on the Cineca Marconi 100 facility. We basically were able to run 240 different training experiments in parallel from the user laptop to the Marconi 100 HPC, and we obtained a 92% speed up. So we took 3 hours instead of 288 hours on a single V100 GPU. And then we also introduced a way to manipulate gather and scatter execution by transforming them into direct communications between nodes. And with this optimization, we were able to obtain almost the same performance of a direct HPC execution. So by going to the SSH connection directly on the terminal and schedule the experiment. And we were able to obtain almost the same performances by using the Jupyter Workflow web interface, so hiding all the complexities of the HPC interaction by simply automatically optimizing the workflow diagram. So this is all for today. I will thank you everybody for listening to my presentation. And if there are some questions, I will be happy to answer them. Thank you very much.
Thank you, Jacopo. Thank you for this very interesting presentation. What I like about those EUPEX webinars is that each time almost we get also the complete picture around the day's topic, not just focusing on one app or one tool, but the complete picture. That's really interesting. So thank you again. And now if you have questions, you can either enter them in the chat, or you can raise your hand and ask your question, whichever way you prefer. So do we have questions? Don't be shy. Okay, we have a message from Mate. Yes,
I don't know how to raise the hand, Pascal.
Okay, well, someone found out how to raise their hand. Can we start with Philippe? Philippe Couvet, who raised his hand, and then Fabrizio. We'll have you. Okay, Philippe, do you have a question?
Yes, you can raise your hand in the reaction menu at the bottom of the screen. I
found it. You are smarter than me, Philippe.
So thank you, Jacopo, for the presentation. I have a question about the first part where you presented results from on workflows executed purely on HPC or cloud, and then compare the mix. It looks like there's no overhead due to the data transfer. So was it because the data transfer were negligible in size or not taken into account?
So the point is that in that case, we did an examination of the workflow. We examine all because when you have one step and the subsequent step, you always have to rely on data. But these data tend to be smaller and smaller as long as you proceed in the workflow, because the majority of workflow tend to synthesize the data and not to produce more data than the input ones. So the point is to find the best place where to split the workflow when you change the facility. In that case, we choose that particular point because the data were small enough to be transferred without huge overhead. But this is always a trade-off. So you can save data, you can save time by moving the data and compute things on another place because you add computing power, you have better computing power. Or you can save time by sticking on the same facility and avoid the data movement overhead. For example, in the federated learning approach, this is particularly evident because you don't move the data but move the model. In the federated learning, basically you cannot move the data for privacy, but also for performance. Why not? There are some techniques like DLOCO that adopt federated learning approaches for performance. And in that case, it is particularly, it is perfectly fine to move the data because normally the model weighs far less than the data. Even if with very large models, this is not so true anymore, because if you try to move a 1 terabyte model, this is still a huge effort. So the point is always to keep the steps long enough to balance for the data movement overhead. This is the reason behind hybrid workflows. They are not always, they cannot always be used. They are useful in those cases, and in those cases, they help a lot. But this is the most complex part of properly handling hybrid execution environments.
Okay, thank you. And one more question about that. When you decide, because it's interesting to move the data from one side to, or from one environment to another one, how do you describe, how do you set up you pack the data so that then you can easily transfer them? I mean, do you have any file system, dedicated file system to store them and then move it? Yeah, how do you describe it in the workflow language?
So we try to move them from one facility to the other directly, and this depends on which is the underlying technology. So StreamFlow supports plugins, so you can do the very base path is to transfer them by tarring on one place and untarring on the other place. This is because tar is universal. But tar is not that fast. So this is why you can always provide another plugin with, for example, use this, I don't know, Grid FTP or, I don't know, direct RDMA if you have it. So a plugin that can speed up the things. But it depends really on the availability of technologies and in the facility, because you don't always have so this is, if you want, a different approach from the grid computing. Grid computing assumed that all the involved machines were speaking the same protocols to allow data movements, for example, through grid FTP or resource allocation and stuff like that. StreamFlow instead adopts a very basic worldwide approach, which is star, and then allows for specific case optimizations when it is possible. Now, this is the reason.
Thank you. Thank you very much.
Thank you.
Okay, Fabrizio, you had a question?
Yes.
I like your screen, your background.
It's a wishful thinking more
Yes,
than a reality,
exactly. That's what I
unfortunately.
meant.
Yeah. Grazie, Jacopo, for your presentation.
Very good.
I am not an expert of CAPIO, I say it up front, but why did you select CAPIO as a library?
So first I'm not that that fair in judging because CAPIO is produced in our research group, so I'm a bit trying to
Biased, you
use
mean?
what. So
That's why
I
I
try
asked
to
Jacopo.
I try to value what I do, but this is like in-house production, no? The slow food principle. Then the other thing is that because this is because CAPIO is very versatile in his approach, because it basically allows to be run totally in user space. So you don't need any kernel modification, kernel drivers and stuff like that. You are able to basically modify the way in which applications exchange data without changing the applications. And this is something which is crucial because no one wants to modify its application, especially it is written in Fortran 77 with fixed line space and blah, 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 because nobody knows exactly what the application does anymore. And the third thing is that when you are not tied to an API, so you don't have to modify your code, like for example, in other libraries like Adios or HDF5 based libraries and so on and so forth, you can always stick with the state-of-art technologies without having to modify also your code. So business code is there and you improve the business code with business algorithm. And then you improve the data exchanging library with data exchanging techniques. For example, if tomorrow you are able to achieve direct RDMA between different Euro HPC data centers, then you encapsulate this on the networking library, which is CAPIO, and you leave the applications as they are, but you obtain a huge improvement of streaming performances for free. And then you achieve this together with all the applications that use CAPIO. So you don't have to modify app A, B, C, D, F. You just modify CAPIO and then all comes for free. This is why we designed this in this way, basically.
From the operating system point of view, the only support you need is MPI to let the system talk. Okay, so basically you piggyback over the existing MPI implementation. You do not require any strange protocol.
No, exactly. Now we are also substituting this MPI-based backend with a multi-protocol backend that supports also TCP/IP and MQTT. And we are also working on, but this is a very new idea. We didn't begin yet. We are working on supporting user space TCP/IP stack through the DPDK library to be able to be as general as TCP/IP is, but without the burden of kernel user space jumps that make it very slow. But this is a very new idea, but the focus here is that you don't have to touch neither the applications nor the part that intercept the system calls. You just have to work on the networking part of CAPIO, and you can experiment with whatever you want. So this
Good.
is
May I ask another question, Pascal?
Yes, we still have time.
Okay, on which platforms did you test CAPIO? I mean, x86, I give it for granted. ARM, RISC-V.
So we tested it on mainly on Intel, so and AMD, so
x86.
x86, yes. We ported recently because the only part that is really changing is the interception system called interception library, which is assembly based. So we first used the x86 also because the majority of HPC now is still on x86, but we recently ported it to RISC-V, and we are now working to the ARM porting, and we will be able to finish the ARM porting inside the EUPEX project because this processor will be ARM based. So we will run on. We will be very happy to test it on large Grace Hopper partitions one day, and also we will be very even happier to test it on very large European processor partitions. But for now, we tested it mainly on x86 and on on x86 at scale and on RISC-V at a much smaller scale. If their project will finish, we will be very happy to test it also on RISC-V HPC partitions. We will see what happens.
Okay, my last question, and I tell you that it is my question. Do you need to have the same ISA on the system you are talking, or because of the MPI layer, the receiving, the producer and the receiving system may have different ISAs?
They can be different for sure.
Okay,
because we allocate
MPI.
one server on the exactly. We allocate one CAPIO server on each machine, and if you compile different CAPIO servers with different ISA, target ISA, then they are perfectly able to talk. The point is that the very risk of doing this is that if the different processors go at very different speeds, you will have still large waiting times, because when you have streaming producer consumer, if they go at very different speeds, then this is you create an overhead. And this is not a limitation in principle, but if you compare state-of-the-art x86 with the state-of-the-art RISC-V nowadays, for example, this is still a problem. Maybe because maybe not that much on the hardware, but on the level of maturity of application porting on different ISAs, especially the HPC ones.
Thanks, Jacopo, and thanks, Pascal.
Thank you very much.
Thank you. I don't see any other question coming in. So I think I will. You still have time for one more question. So if someone wants to ask a question, please raise your hand or enter it in the chat. So while we're waiting for a potential last question, I would like to announce the next webinar. So please remember to register for our March webinar, which will be on the 26th of March, vectorization of FEM kernels. You'll find the registration link either on the EUPEX website or on LinkedIn. We're on LinkedIn. All our events are announced on LinkedIn. And still no questions. So I would like to thank everyone. Thank you, Jacopo, for the very interesting presentation. Thank you, Fabrizio and Philippe, for your excellent questions. It's always nice to be able to exchange with the audience. That's why we do webinars. So, and thank you, Matteo, for your kind words. So thank you, everyone, and hope to talk to you again in March. Bye-bye.
Ciao,
Thank you,
everybody.
Ciao, ciao.
Ciao, Jacopo.
Ciao.